Hello. Today we are going to study, discuss, analyze the next portion of matrix theory. In the last session we have discussed what is a matrix, the addition properties of matrix, subtraction of matrix, types of matrices, null matrix, column matrix, row matrix, scalar matrix, diagonal matrix and all. Now as we have understood the importance of matrix in business mathematics, we are going to indulge upon the multiplication aspect of matrix theorems. The multiplication aspect is necessary in order to apply the concept of matrix to various different case scenarios that arise in case of doing a business, running a factory. A lot of applicative activities can be taken upon through the help of multiplicative model of the matrix. But how the matrix multiplication is possible? What are the basics that should have been dealt upon so that we are able to deal with the multiplication of matrices? We can multiply two matrices if the number of columns in the first matrix is the same as the number of rows in the second matrix, which means, because we have already know that the order of matrix is m into n, if the number of rows in the matrix is 3 and columns is 2, it can be multiplied with a 2 into 3 matrix which is having opposite number of rows, that is 2 rows and 3 matrices. So number of columns in the first matrix should be exactly equal to number of rows in the first matrix. That is when matrix multiplication is possible. Example, multiplying a 2 into 3 matrix by a 3 into 4 matrix is possible because the number of columns in the first matrix is exactly similar to number of rows in the second matrix, and what we get is a 2 row 4 column matrix, 2 into 4 matrix. But a 4 into 3 matrix cannot be multiplied with a 2 into 3 matrix because number of columns in the first is not equal to number of rows in the second matrix. So we must remember that number of columns in the first matrix must be exactly similar to number of rows in the second matrix. But how should we multiply the matrices? Let's take a general 2 into 3 matrix multiplied by a 3 into 2 matrix. You can see that matrix A involves 2 rows and 3 columns. Matrix B involves 2 columns and 3 rows. So number of columns in the first matrix is equal to number of rows in the second matrix. First matrix has 3 columns and second matrix has 3 rows. They can be of course multiplied, resulting into a 2 into 2 matrix. So we'll find AB by multiplying a matrix A with matrix B. We take A and B. First of all, we will multiply the first row of A with the first column of A. We know that multiplication of a 3 into 2 matrix is possible with a 3 into 2 matrix, As a result, there will be a 2 into 2 matrix, number of rows equal to number of columns. So here the resultant answer would be a 2 into 2 matrix. So we will have 2 rows and 2 columns in the new multiplicative matrix. We first multiply column row of matrix A, first row of matrix A with the first column. Then you multiply first row with the second column and write it in the first row. So A multiplied by U plus B multiplied by W plus C multiplied by Y, it will come as A11. Then we multiply A into B plus B into X plus C into Z. Next we multiply second row of the first matrix A with first column of second matrix B and then with second column of this matrix B. So DEF multiplied by UWY, so D into U plus E into W plus F into Y. It will come in the second place in the first column, or the second row, first place in the second row. Next we multiply DEF with VX and Z, D into V plus E into X plus F into Z. We add them all together, we get the resultant answer AU plus BW plus CY, AV plus BX plus CZ. Then in the second row we have DU, EW, FY, all of them added together, DV plus EX plus FZ. So we have seen how the matrix is multiplied. Now we come to another example. This example of course doesn't contain the letters, it has a number example. It contains numbers, of course having the same order, that the first matrix is a 2 into 3 matrix and the second matrix is a 3 into 2 matrix, so they can be multiplied. Here also we take the same route, that the first row will be multiplied with the first column, then with the second column, and it will be written in the first row one after another. Then the second row will be multiplied with both the columns and it will be written in the second row. So 2 into 3 multiplied by 4 into 4 minus 4 plus minus 3 into 1. Then 2 into 5 plus 4 into 2 plus minus 3 into 3. Then the second row will be multiplied with both the columns. 1 into 3 plus 5 into minus 4 plus 2 into 1. 1 into 5 plus 5 into 2 plus 2 into 3. Adding and subtracting each other, we get 6 minus 16 minus 3, that is minus 9. 10 plus 8 minus 9, that is 9. 3 plus 2 minus 20, that is minus 15. 5 plus 10 plus 6, that is 21. So the resultant answer matrix AB is minus 9 and 9 in the first row and minus 15 and 21 in the second row. So first of all we have seen how the letter matrix is multiplied, and now we have seen how a number matrix has been multiplied with another number of matrix. Now we come to a 3 into 3 matrix, matrix A multiplied with matrix B. This is a 3 into 3 matrix multiplied with a 3 into 3 matrix. The resultant answer is going to be a 3 into 3 matrix. The first row multiplied with all the columns, second row multiplied with all the columns, third row multiplied with all the columns. The first row has been multiplied with the first column, it is written in the first row, first place. The first row again is multiplied with the second column, written in the second place in the first row, and the first row has been multiplied with the third column and written at the third place in the first row. Then the second row has been multiplied with the three columns and written in the second row consecutively. Then the third row has been multiplied with all the columns and written in the third column, written in the third row. So we have got all the three columns and three rows. So we have 3 into 3 matrix. The answer is 43, 85, 41, 28, 52, 44 and 27, 82, 49. So you can clearly see that when the first row is multiplied with the first column, the resultant answer is written in the first row, not in the first column. So you must remember that. The second row multiplied with all the columns will be written as the second row. The third row multiplied with all the columns will be written as the third row in the new matrix. So AB is a 3 into 3 matrix. Now there is a little variation in the next example. A matrix of the order of 3 into 3 is given, and another matrix B of the same order has also been given. We have to find by operations of matrices 2a plus 3x is equal to 5b. We have 2a plus 3x is 5b, so we can subtract that from the other side. 2a plus 3x minus 2a is equal to 5b minus 2a. We subtract 2a from both the sides. So 2a plus minus 2a gets nullified. So we have a 0 matrix plus 3x is equal to 5b minus 2a. So x is equal to 5b minus 2a divided by 3. A null matrix or 0 matrix doesn't have any answer. So 3x is 5b minus 2a, which means x is equal to 1 by 3 of 5b minus 2a. So we can put the values. This is a scalar multiplication. We have already done it. So this can be written as this: 1 by 3 of 5b minus 2a, 1 by 3 into 5 of a, 5 of b, pardon, and minus 2 into a. We multiply the scalar value of 2 into b and 2 into 5 into b and 2 into a. We find 5b minus 2a as 135, 23, 3, 19, 7, 22, 25 and 4. Then we take the 1 by 3 portion, divide all the resultant numbers of the new matrix by 3. So we have the answer of 2a plus 3x is equal to 5b. So the matrix X is given as 1 by 3 of 5b minus 2a. Now we have seen a little bit of the multiplicative theorem. We should be in a position to understand the multiplicative properties of the matrices. First of all, we're going to discuss and understand the associative law. We have already done that for the matrices of the additive law. A plus b plus c is equal to a plus b plus c. Of course, under the bracket here, if there are three matrices A, B and C, we multiply AB, then multiply that with C, it will be exactly equal to A multiplied by BC. So this is an associative law that AB multiplied by C is equal to A into BC. The distributive law is almost similar as the multiplicative number. A plus B multiplied by C is equal to AC plus BC, where both the sides are equally defined. The existence of multiplicative identity for a square matrix A, square matrix means of the order of 2 into 2 or 3 into 2, 3 into 3 or 4 into 4, there exists an identity matrix of some order where I into A, identity matrix into A is equal to A into I is equal to A. When you multiply the identity matrix with a matrix A of a square matrix of an order of m into n, which is where m is equal to exactly equal to n, then identity matrix multiplied by that square matrix will be exactly equal to the same matrix which is given. There is an example which we are going to undertake and discuss. There are two farmers, Ramkishan and Gurcharan Singh. They cultivate three types of basmati rice. They sell in rupees, and the sales of 2 months, September and October, are given. The September sales in rupees for three types of the rice, basmati, parmal and nora, is given for both the farmers, Ramkishan and Gurcharan. Ramkishan is given in the first row, Gurcharan is given in the second row. 10,000 for Basmati, 20,000 for Parmal, and 30,000 for Nora. This belongs to Ramkishan. 50,000, 30,000, and 10,000 respectively belongs to Gulcharan. Similarly, in the lower end, the matrix B denotes the sales of both these farmers for the month of October. We have to find the combined sales in September and October for each farmer. Combined sales, so we have to add it. We also have to find the decrease in sales from the first month over the second month, so we have to subtract. How this is done? Combined sales, we have to add both the matrices, corresponding number with the corresponding number in the second matrix, 10,000 plus 5,000, 20,000 plus 10,000, 30,000 plus 6,000, and so on. We have A plus B. Now the second answer is change in sales, which means how much the sales has decreased or increased over the month. We have to subtract the first from the first matrix the second matrix, that is A minus B, which is 10,000 minus 5, 20 minus 10, 30 minus 6, 50 minus 20, 30 minus 10, and 10 minus 10. So if you can see, in case of Basmati, the sales has decreased considerably. From 10,000 it has come down to 5. So overall, for Gurcharan, the decrease is very severe in Basmati. It is a little bit less in the second variety, but there is no decrease or increase in the third amount. But for Ramkishan, who is the first farmer, there is an absolute decrease in all the quantities, all the types of the rice that he is producing. Now we are coming to another example. In a legislative assembly election, a political group hired a public relation firm to promote its candidates in 3 ways: by making telephone calls, house calls, and letters. The cost per contract is given. For a telephone call, it costs 40 rupees, house call, it costs 100 rupees, and letter 50 rupees. The number of contracts that is made by the peer firm is given as follows. For X and Y, 2 cities X and Y, 1,000, 500, and 5,000, 3,000, 1,000, and 10,000 for Y. We have to find the total amount spent by the group in both the cities. We have to calculate BA, second matrix, because we have to calculate BA and not AB, because in the first matrix the number of columns is 1, and in the second matrix the number of rows are 2, so it cannot be multiplied. So we have to multiply it otherwise. If the number of columns in the second matrix is equal to number of rows in the first matrix, so that is why we are multiplying BA, because AB in these circumstances is not possible. So 1,000, 500, 5,000, 3,000, 1,000, and 10,000 multiplied by 40, 100, and 50. So respectively we get a 2 into 1 matrix. So for city X, the total amount of money spent is 3,40,000 paise and 7,20,000 paise. That amounts to 3,400 rupees and 7,200 rupees respectively. Because the cost per contract is given in paise, so we have to convert that into rupees. So the amount of answer is given in rupees is 3,400 and 7,200 respectively for both the cities. So here the point to remember is that we will not be able to multiply A into B, so we cannot, and we are not in a position to calculate AB, so we must reverse the matrix. So we are calculating BA. That is perfectly possible. Now we have come to a stage where we can understand and discuss advanced theories in matrix theory. This thing is transpose of a matrix. When a matrix obtained by exchanging the rows and columns is found out, it becomes transpose of a matrix. It is written as, if matrix A is there and we are finding a transpose of the matrix, it becomes AT, transpose of A. For example, matrix A is given. There are 3 rows. So in the transpose matrix AT, we will convert the rows into columns and columns into rows. So 2, 5, 6, which is the first column, first row, becomes the first column. 1, 3, 4, which is the second row, becomes the second column. 4, 5, 3, which is the third row, becomes the third column. So simply replace the rows by columns or columns by rows. The transpose matrix is the original matrix. The transpose of AT is A. A scalar number multiplied by A of transpose will become equal to scalar number multiplied by the A transpose. K is known to be any constant number, 5, 3, 7, whatever. A plus B transpose is exactly equal to A transpose plus B transpose. A plus B transpose. The next is AB, multiplication of A and B. If you find the transpose of AB transpose, it is exactly equal to A transpose multiplied by B transpose or B transpose multiplied by A transpose, whatever is possible under that circumstances. Now we have come to understand symmetric and skew symmetric matrices. A square matrix is said to be symmetric if the A dash of that matrix or A transpose of that matrix becomes exactly equal to the original matrix. You have taken a matrix on the screen on the slide, root 3, 2, 3, 2 minus 1.5 minus 1, 3 minus 1, 1. When you calculate the A transpose, you find that even if you have converted the rows into columns and columns into rows, the matrix remains the same. So A is a symmetric matrix as transpose of the same matrix is exactly equal to the same matrix. So a square matrix A is a symmetric matrix because transpose of A is exactly equal to A. But a square matrix A is said to be skew symmetric if A transpose is exactly equal to minus A, not A minus A. Now we have come to discussing the point which is very important from the perspective of matrices, the invertible matrices or inverse of a matrix. I will make it clear from the beginning that inverse of a matrix is possible only if the matrix is a square matrix, M is equal to N. Inverse of a matrix is going to be calculated if the matrix is a non-singular matrix, which means if the determinant value of the determinant is not equal to 0, we will be able to calculate inverse of a matrix. For example, A is 2, 3, 1, 2 and B is 2 minus 3 minus 1, 2. Now AB is equal to 1, 0, 1, 0, which is equal to a identity matrix. Similarly, BA is equal to an identity matrix. So in that case, B is the inverse of the identity matrix. So B becomes an inverse of matrix A because from the functionality BA is equal to AB, which is also equal to an identity matrix. In other words, B is A inverse and A is B inverse. Now we have to find the value of x and y from the following equation. We have now we have an example to prove the associative law of the matrices. We have been given 3 matrices A, B and C. We have to prove that A into BC is equal to AB into C. We have been given 3 matrices. The first matrix is a 3 into 3 matrix, the second matrix is a 2 into 3 matrix, and the third matrix is a 4 into 2 matrix. First of all, we'll calculate AB, matrix A multiplied by matrix B. First row with first column, first row with second column, second row with first column and second column, third row with first and second column. We are getting AB to be 2, 1, minus 1, 18, 1 and 15. Now we'll find AB multiplied by C, that's the resultant answer, multiplied by matrix C. First row by first column, first row by second column, first row by third column, first row by fourth column. We have 4 numbers respectively. Then we will multiply the second row with all the 4 columns, write it in the second row. Then we are going to multiply the third row with all the 4 columns and write that in the third row. We get AB multiplied by C. Now we go to the next slide. We have to find BC first. We multiply matrix B with matrix C, which is first row with all the 4 columns, second row with all the 4 columns, third row with all the 4 columns. We get BC. Now we multiply BC with A. First row 3 numbers with first column, first row 3 numbers with second column, with third column, with fourth column. Write that in the first row of the resultant matrix. Similarly, we multiply second row with all the 4 columns, write that in the second row of the new matrix. At the end of the multiplication, we multiply the third row with all the 4 columns. We get the numbers. Now we can see with the previous answer that AB multiplied by C is exactly equal to A into BC. So associative clause, we proved that AB multiplied by C will always be equal to A into BC. So we proved the answer. I've given you one unsolved question, which is A is 067, minus 608, 7 minus 8 and 0, B is 011, 102, 120, and C is a singular matrix. It has only one column. It is a column matrix. We have to calculate AC, BC and A plus B multiplied by C. Also verify that A plus B into C is equal to AC plus BC. I have given you the answer of AC plus BC, so you can calculate at home and verify the answer. I hope that you would be able to do that and you get the right answer. In case you have a wrong answer, you don't understand, you must come back to me for a clarification. Now we have another example where a matrix A is given to be a 3 into 3 matrix, and we have to calculate A cube minus 23A plus 40I is equal to O. It's a null matrix. We cannot multiply a matrix 3 times, so we have to multiply it twice, get A square, then multiply that with A, we will find A cube. So A square is A into A, same matrix multiplied twice, we get 19, 4 and 8. Here also we fundamentally follow the same principle. First row multiplied with 3 columns written in the first row of the resultant matrix, second row multiplied with the 3 columns written in the second row, third row multiplied with all the 3 columns of the second matrix and written in the third row. So we get 3 rows of 3 matrices. Then we find A cube, which is A square, which we have got in the first multiplication, A square into A square 19, 4, 8, 1, 12, 8, 14, 6, 15 multiplied by 1, 2, 3, 3, 2, 1 and 4, 2, 1. We get 63, 46, 69, 69 minus 6 and 23, 92, 46 and 63. We get 3 into 3 matrix. Now we come to the identity matrix, that A cube we have already got, 23A is scalar number 23 multiplied by A, matrix A, and 40 multiplied by identity matrix. Identity matrix is a diagonal matrix whose diagonal numbers are exactly equal to 1. So 40 into the diagonal matrix, scalar matrix that is. Now the first A cube is given. We multiply 23 with each element of matrix A. We get 23, 46, 69. You have to multiply the numbers respectively with the numbers which are given. 69, 46 and 23, 92, 46 and 23. Then we get 40, 0, 0, 0, 40 and 0, 0, 0 and 40. Now from the first matrix, we subtract both the other matrices. The first number is 63 minus 23 minus 40, that is 0. 46 minus 46 is 0. 69 minus 69 is 0. 69 minus 69 is 0. Minus 6 plus 46 minus 40 is 0. Then we have 92 minus 92 is 0. 46 minus 46 is 0. Then we have 63 minus 23 minus 40, which is also 0, which is exactly the answer is coming to be 0 matrix. So what we are asked in the beginning is that we have to prove that A cube minus 23A plus 40I is exactly equal to 0. So we have proved that is coming to be a null matrix. So we have concluded a lot of things from our discussion, and we have come to the end of this session. But you must remember that matrix is a very important topic in business mathematics, and because matrix has the capability of converting very complex data set to simpler forms, and various applications can be made. Of course, we are going to take a particular session for studying applicative portions of the matrix theorem. So we must remember that till we come to that. But before doing that, we will be doing inverse of the matrix and Cramer's rule in detail. And we must not forget that these things are very important from the point of view of uh, calculative parts. And matrix is an alternative to linear programming really in actual life. Linear programming is too complicated. It requires software forms. Even if somebody is sitting down and trying to calculate the answers, linear programming is actually too cumbersome, time-taking procedure. So matrix and determinants are a simpler form of alternative to those difficult operation resource things. So I hope and I sincerely do hope that you are able to understand whatever we have done here, and you are going to practice it at home so that you come prepared, better prepared in the next session, so that we can discuss a lot of other things which will come up by then. So till then, I hope you have understood that. We will be continuing from here whatever we have studied, and whatever is required to remain to be studied will continue from there only. So till then, thank you very much, and hope to see you again very soon.